So thank you very much for being here, and I hope you can all hear me well. I'm trying to come up with some extra voice here to overcome the sleepiness that might affect you after this wonderful meal. I'm Andreas Zeller, and I'm from Saarland University. I'm also from the Center of IT Security in Saarbrücken. This is the center. In a couple of weeks from now, I will move exclusively into that center and away from Saarland University, as is this entire center, because the center has turned into a so-called Helmholtz Institute. If you have not heard about a Helmholtz Institute in computer science, that's because there is none yet. And this new Helmholtz Institute will focus on IT security with a base funding for 500 researchers. We're talking about a yearly base funding of 50 million euros, guaranteed for the next 30 years, which is a very significant investment. And I will lead, I think, the group on mobile security and autonomous systems. But this is just one of the areas that I'm supposed to take care of. In fact, I can do whatever I like, except that I will do less teaching than before, which is probably great. And in terms of, and the reason why I, as a software engineering person, moved over to the Security Institute is that actually my work became more and more relevant for security. When I was some 25 years ago, when I was still a lowly PhD student, one of the techniques in testing that interested me most was the concept of fuzzing. That is, you generate some random input, which you then happily feed into some random program to see whether it crashes. This, for instance, this is a random input, but it may also be a valid Perl program, for instance. So you could easily feed this into a Perl interpreter to see what it's doing. And the fun thing about these techniques is that they are super simple. And they're super simple to apply. You actually don't need a PhD or anything. You don't need formal methods or something. And the first experiments with fuzzing, this is now some almost 30 years ago by Bart Miller in Wisconsin. When he first tried that out, he could be seen as the father of fuzzing. He was able to break 25 to 33% of Unix utilities, which today would probably take the end. If he came up with a similar result today, this would probably be the death of the internet as we know it. So this was quite an event. Of course, coming up with such a very simple input, such as this one, is something that requires 10 lines of code, and this is commonly being done. And most of the existing programs that you know of are easily subjected to such input. But the problem is, if you come up with something that is more complicated, that takes an input that is better structured, anything that requires a parser typically will happily reject any invalid input and do so by the millions. And it's very hard if you want to get past the parser deeper into the program with fuzzing. You need to come up with something that would be accepted by the parser. That is, you need a syntactically correct input. This was explored now 5 years ago by a student of mine named Christian Holler. He built a fuzz tester based on grammars. I suppose you all know grammars, as of now they're still material of the first year in computer science. And the idea is that this generator would take a grammar to generate inputs as well as to parse existing inputs. And we applied this on JavaScript interpreters. So here's a typical JavaScript grammar. You see, you all see such grammars before. You have an if statement, and if statement either is if followed by an expression followed by a statement, or you can have if and an else in there, so the else is optional. You have switch statements and everything. And Langfuzz uses this grammar both to generate inputs as well as to parse existing inputs. And here's one of the inputs that Langfuzz generated. This is a synthesized JavaScript program. And this simple JavaScript program in 2012, in line 8, happily crashed the Mozilla JavaScript interpreter. This is an original slide taken from the presentation of Christian Holler at Usenix in 2012, when he was showing off how his JavaScript fuzzer would find bugs in Google Chrome and in Mozilla. And in the course of 9 months, which was between starting the thesis and presenting the work, he actually got 30 security rewards and bug bounty awards. And the number that is most memorable is this number. In the first 4 weeks of running his tool, he netted $50,000 in bug bounties. This is a slide I always put up when I want to get students into my courses. Because actually, right now I am running a course on security testing and fuzzing, and I'm always pointing out, $50,000 in first 4 weeks, beat that, and you get a great grade. You also get lots of money on top, so that's a great thing. By the way, if you ask what did he do after the first 4 weeks, he got hired away by Mozilla. And as of now, we just had him as a keynote speaker at ISTA last year. As of now, his tool has found more than 4,000 bugs, 4,000 separate, confirmed, fixed bugs in the JavaScript interpreters of Mozilla and Chrome. So if you use Firefox or Chrome next time, the reason why this JavaScript works is to a significant part because of the interpreter having been very thoroughly tested. Since then, after a couple of years in other research, we have now started getting back to this idea of grammar-based fuzzing. What we have completed at this point is a nice tool called Tribble, which is also a grammar-based fuzzer. That is, it takes a grammar and uses the grammar to produce inputs to other programs. So far, so good. But with the experience that we have gained in search-based testing, among others, in symbolic testing, and you've seen already Shiva and Paolo tell you about that, we are also now able to use a couple of extra tricks. We can use grammar coverage to guide the test generation. We can use feedback from the program towards a particular goal to guide test generation. And this is a trick we learned from blank fuzz again. We can also make use of existing input samples in order to get fragments as well as probabilities. We can learn how frequent particular parts of the input are and use this to guide the search. And generally, this whole framework allows us to produce inputs, to parse existing inputs, to mutate them, and to recombine them. What do these individual parts mean? Well, the intuition is fairly simple. Grammar coverage. This is a concept that is so simple that I was very amazed. So we haven't found this before. Here's a grammar for arithmetic expressions. And the idea is very simple. Whenever you have the choice between multiple alternatives as it comes to producing things, you go for those parts which you have not produced yet. That is, for instance, when you have to produce a digit, and you've seen you produced a 2 before and a 5 and a 6 before, well, you go for something that you haven't seen yet. And this then, if you keep on doing this again and again, this is going to get you inputs that are very diverse. For instance, they have multiple unary operators, they have multiple dual operators, and of course they cover all the individual digits, and they also cover floating point numbers as well as integer numbers. All of this simply by applying this coverage concept on the grammar, which already gives us much better diversity than what other producers, in particular tools like LangFuzz, did. And this is 5 lines of Python to implement this. Another interesting concept is code coverage. And you've already heard from Shiva and from Paolo the general idea that you have a particular target in mind when you want to cover, that you want to get as close as possible to. And we are not particularly creative in this point, but we adapt existing approaches. So we also have so Tribble also comes with a nice genetic algorithm. We create a population. We can create mutations. We can recombine things, and then we rank them according to the goal that we want to achieve. And this then allows us to come up with a better population. The interesting thing, though, is that all of these operations now are grammar-based. If you want to do a mutation based on a grammar, well, you replace one term by a syntactically valid other term. That's generic. If you want to recombine things, you have 2 inputs, and then you can again exchange things based on the grammar. And since this is all based on grammars, you can write a grammar for a scenery for automotive testing, for instance. and then use the grammar to create all sorts of sceneries. This is all generic. Or you can use a grammar to, well, why not, invoke individual functions, and then you have something like AvoSuite. Or you can use it to describe network inputs, for instance, and then you have all the individual constituents of a network input. And all of these features that were built into Tribble therefore become generic. You can apply them to anything that can be described with a grammar as is. And also, what also comes as an extra, as a population, you could also use an existing population. If you do have an existing population of inputs, and in many fields, you have for many fields where there's programs, there's also inputs to these programs. You can use this population then again to optimize towards a particular goal. All this comes naturally when you have a grammar, because a grammar both gives you the parser as well as the means to produce it. And this then allows you to also allows you to guide the generation towards likely inputs, towards unlikely inputs. So all of this comes naturally when you have one common model that is general enough in there. However, all of this requires that you do have a grammar in the first place, and that's actually not an easy task. My student Christian, who built this for JavaScript, this is an abstract view of Christian doing this, actually spent 2.5 months building a grammar for JavaScript. You would imagine there would be one. No. There is a sort of informal description of what JavaScript is, and there is the implementation in the interpreters. And coming up with a grammar that would be generic enough to actually be used again and again at the time was actually pretty hard work. So what we have been focusing on in the last 2 years, besides making the production better, is a field that is actually normally a well-established field in artificial intelligence, which is called language induction. You have a sample, and you want to know what is the structure of this sample. So look at this sample input, for instance. You may be able to recognize this as a human. You see this as the URL. You have an idea of what a URL looks like. The interesting twist that we do to that, though, is that we use a program. That processes the input in order to learn what the structure looks like. And this is an idea that can take you very, very far. Let's take an example. So again, we have this URL. It consists of a protocol, then you have a host name, you have a port, you have a login. Don't use logins in URLs ever, by the way. They are transmitted in the clear. But they're part of the standard, so they're also part of URL. You have a page request, and all of these are separated by individual symbols. Now, if you look at how a program processes all this, how does it do that? Well, it takes the protocol in order to understand how the rest is being parsed. Then it connects to the host name. It converts the host name into an IP address, and then connects to the host at that IP address on that port. Then if there's a login, it sends the authentication information, and then after authentication, it sends out the page request, and then it gets the page back. So the interesting thing here is that each of these individual parts of the input is processed in different functions, because, well, the host name goes into a DNS resolver, the login gets sent over a connection, so all of these take different paths, and they would therefore also be stored in different variables, to start with the arguments of these very functions. Okay? So the idea is that we track the input in order to figure out for each character where it's being processed, and this then allows us to infer a grammar from that. We have two means of doing so. We have a precise one and a robust one. The precise one uses so-called dynamic tainting. This means that we attach a tag to individual values while they're being processed, and this tag then propagates along all the individual operations. So whenever some value is derived from a character, the tag representing the origin gets passed on to the derived value and further on during the computation. The second method is an easier one. It's robust. It's not as precise, but it works amazingly well. This is simple. We look at the program execution. we look at all the variables that are strings, and we check those strings whether they hold parts of the input. And if they hold parts of the input, if you find a variable that has a value HTTP, and some of your input also has HTTP, then you assume that this variable comes from the input, which may or may not be valid, but it works. But simply checking input is far easier than implementing a full-fledged dynamic tainting framework. We implemented, and I know what I'm speaking of, we implemented a full-fledged dynamic tainting framework for Java, and we found dozens of bugs in the JVM with that. Millions of new ways to crash the JVM machine. Recognizing inputs is a far more robust method. How does this work? Well, 2 steps. How do you infer a grammar from an input? Well, there's a super easy method. You simply say the grammar is exactly this input. That's a trivial way. Okay? I simply say the grammar consists of this one input, and there we go, we have a grammar. That's, technically speaking, that's correct, but that's not what you assume a grammar to be. So what we do in the next step is we check, we take the values and variables that we found, namely these, and then we check whether the values occur somewhere in the grammar, and if they do, we replace these concrete values by symbolic names derived from the variable names. Let me illustrate this with an example. Here's a variable, netlock, and this is the value. And we find that this string exactly occurs up here also in our grammar so far. So what we do is we replace this by a symbolic netlock, which is this, and we add a new rule that netlock now can expand to this string. We can do the same for the scheme, and then we get a new rule for scheme. We get a path, and the path is up here, and we have a fragment up here, and we also have a variable which is weirdly called URL, which also holds path. Well, we can still apply this, and then we get an interesting rule that the path is the URL, and the URL is /path. Now, technically speaking, this is still the same input as before, but now we know the structure. We see that there's a scheme, there's a netlock followed by a path, and all that, and this is something we can now happily exploit. And I'll be happy to show you how this works in a demo. Turns out I'm actually, as I said, I'm teaching a course on security testing, and it turns out that these techniques of mining a grammar actually fit into an amazing small program. I've come up here with a little Python program that does this whole job in approximately 200 lines of code, and it took me 4 hours to implement this. And that's not because I would be a genius, it's simply because once you know how to do it, it's not very complicated anymore. So I'm just going to run this thing and show you what it does. First thing is, we have a function called URL parse, and in Python it's very, very easy to access the values of variables as the program is executing. There is a nice little function called, which is called setTrace, and there you can pass a function named traceIt, which will be called for each and every variable. For each and every line of the program as it's being executed. And this trace function actually gets one parameter, which is the current frame with all local values, which you can then access as Python objects. So you simply iterate over them, you access the value, and then we check whether the value is a string. We check whether this is a string of at least 2 characters. If it's just 1 character, there's too many spurious matches. And then we check whether the value also occurs in the input, and then we save it. This is it. This is 10 lines of code. Okay? And this is what we do, and after that we turn off the tracing, and then we have a list of variables. And then we can apply, and this is what we have here. These are the values as found. This is pretty much exactly as we had it on the slide just moments ago. And now I can apply my tiny little grammar algorithm, and here's the first grammar I get. I get start is scheme, followed by netlock, followed by URL, followed by fragment and whatnot. And this is just for one input. Let me come up with more inputs here. Oops, let me just see, where am I? Okay, here I am. So where's my mouse pointer? Here we go. Thank you very much. I can also go and come up with more inputs. So for the fun of it, let's make that Huawei.com, right? Or let's come up with the Chinese one. Why not? Huawei.China. Is that a correct URL? Huawei.China, is that correct?
Yes.
Okay, thank you so much. So I'm going to come up with Huawei.China in here. And let's see whether we can learn a grammar from that. Now I'm going to come up with learning from multiple grammars. And the fun thing is that what you can do there is you learn a grammar for each of the individual inputs, and then you merge them by introducing alternatives, and by introducing alternatives at the rule level. I'm going to show you this directly in the result, what you get here. So now what you have is you have different paths in here, and these paths now become alternatives in the grammar. You have a query, which is always the same, but you have different hosts here, and the hosts also become alternatives in the grammar. The fragment, you have different values here, and these also become alternatives. And the scheme here, and the main grammar, in the main grammar you can see that parts such as the fragment, for instance, are optional because you can also go without them. The query with a question mark is optional because, again, you can also do without it. So simply by looking at these three inputs and tracking the individual variables during execution, we already get an idea of what the input looks like. And now I can use this very grammar, and again in more 10 lines of code, I can use this to fuzz things by turning it into a producer. And here I go, and now I have 100 different combinations of schemes, of host names, of ports, of references, of queries all day long. And I can generate as many as I like from all these concrete values. All of this fits into 200 lines of Python. So that was a bit disappointing, in particular to the student who spent more than a year doing the Java implementation. So this is a technique that works in the small, but it also works in the large, and in the large it works even better. So we built a tool called Autogram, which is a tool that infers grammars that infers languages for Java programs. This is the first technique ever that went and that was able to infer an input grammar from programs. And in contrast to the Python trick that I just showed, it uses dynamic tainting such that it can deeply go into the program in order to recognize structure. It also has a couple of other tricks. It can automatically identify optional parts and repetitions by active learning. This means that it actually tries out for each part of the grammar whether an input that does not have this part actually is a valid input. So for the URL, it takes out the scheme, HTTP, and it has a URL that then starts with : / and checks the program, is this a valid input, yes or no? And, well, it's not, so it's not optional. It also checks for repetitions. So for instance, is it possible to repeat queries? Is it possible to repeat references and others? This is a good question. I don't think, no, this is also not allowed. And it also comes up with a number of predefined lexical items for easy things such as identifiers and integers. Here's a couple of examples for URLs. This is what Autogram produces out of the Java parser for URL. Now with active learning and everything, it takes just this one single input, this one URL, and then it goes and extracts a full-fledged specification out on what makes a URL. You see that it nicely infers that the query is optional. Actually, it's possible to have a question mark and not a query. That's legal. It also infers that the reference here is optional. The protocol is non-optional. The authority is non-optional. The path is. The authority consists of a user info at, this is optional part, the host, non-optional, port optional, and it goes all the way down. So this is a grammar that you can. This is the raw output of the tool, and when my student first showed me this output, which is now a bit more than a year ago, I asked him, "That's very nice, and I'm going to put this on the slide. But can you send me the raw output, please, too?" And then he was a bit puzzled because he said, "This is the raw output, Andreas." And yeah, sure, this is the raw output. This is what you get out of it. And here's another example. This is ini files. Here you can see that the structure of the grammar actually depends on the structure of the program that processes it. Ini files This was for ini files is key value pairs in sections that are introduced with square braces. This is something. This is a parser which actually has multiple functions to do the same thing. So there's multiple functions in there which all parse key value pairs, and this is reflected in the grammar, which now has one part here which does key value pairs, another part here which also does key value pairs. This is something that we could easily fix by finding out that this is actually a subset of this, so we could merge the whole thing. But I wanted to show you this again in the raw form to tell you that if you have a program that is very badly structured, this is going to be reflected in the grammar. But most programmers don't do it that way. And here's another nice example. This is minimal JSON, also in Java. And here's a JSON input. You see, JSON is essentially a key value format again, but it's pretty rich with multiple data types, booleans, various forms of numbers. There's also null, and there's also strings as values, and there's also arrays up there. And the JSON grammar that pops out of that, this is the JSON grammar that pops out of that. And you see, what is a JSON input? It's a value to start with. And what is a value? A value is a string, or false, or true, or an object, or an array, or null, or a number. A string comes in double quotes. False is false, true is true. An object is a curly brace, followed by string internal, colon value, followed by an arbitrary number of more key value pairs, and finally followed by a closing parenthesis. This is textbook quality.
Question. The names of the non-terminals look really meaningful. Do you get them automatically?
Sorry?
The names for the non-terminals look very meaningful.
Yes.
Do you get them automatically?
Yes.
Yeah.
So the names that are underlined in here, these are names that come from Autogram itself. This is what it comes up with a couple of predefined names in here. These are actually wrong. This should be all these other names: string, array, null, number, exponent, fraction. These are names that are derived from variables, as in the Python program, as well as from functions that process them. And in the minimal JSON parser actually has a function called parse object, parse string, parse array, and we make use of all these names. When I presented this work for the very first time, which is now more than a year ago, when I came up with the very first results, I did this at the German National Computer Science Conference, where they had me as keynote speaker. And this was a very wide auditorium. And there also were people in there who worked in language induction. So these are people who work in formal languages. And where in language induction, classical AI thing, there you only have input samples and you want to know what the structure is. If you ever seen, say, the Angloin algorithm, the L-star algorithm, that's a typical example of that. And there's this very small group of people who do language induction for context-free grammars. And they've seen this example and they asked the very same question as you did. They asked, where do you get these names from? And I said, well, we get them from the program that processes it. And then he said, so you have a program? Yes, sure, that's the whole point. So you're cheating. Because from their perspective, if I have a program that processes it, but then in some way there is, the knowledge of the structure is somehow encoded into that program, of course. But the question is, how do you get it out back again? And this is what we have done with Autogram. A couple of peeks into current work. We have now finished a nice tool that does dynamic tainting for C programs, which now allows us to go beyond Java programs to apply Autogram on C programs. This is very exciting because there's plenty of C programs, in particular at the system level, network infrastructure, Unix command line tools, and others that are very exciting. Sample-free learning of grammars. We have a nice little Spike solution that is actually able to learn a grammar even when there's no sample around at all. I'll be happy to talk to you about details on how this works. Guiding fuzzing towards code coverage. This is something we have just completed. Works very nicely. Integration with symbolic testing also is completed. We have very nice solutions on how to get that to scale. And in overall, what we want to build with that is we want to build the world's best fuzzing platform, because we have a general mechanism here, which is grammars, which everybody knows how this works, And we want to integrate the best breed of techniques, such from Paolo and search-based testing and everything, in order to get this to work. And when I'm saying that we build that, actually, these are my students who make it all possible. And yeah, I'm having five PhD students and one postdoc, all working towards the same goal. But even beyond testing, there's quite a number of things you can do when you have this learning of input models, as you can generalize it. If you think about reverse engineering, for instance, you have some unknown input format. You can find out how the input is structured, and it gives you. And since each of these fragments of the input is tied to a particular piece in the code which processes it, this again helps you in understanding how the code works, because you can then tell, okay, this is how my input is structured. Where in the code is the place that actually takes care of the port number? There you go. That's a simple thing. Likewise, if you do have a good, if you do have a good test generator at the system level, this means that you have plenty of valid inputs. This then is a great base for mining specifications, because you can easily cover lots and lots of behaviors. It's actually, so bringing together specification, mining, and test generation requires a very good test generator, and this is precisely what we're building here. Formal verification. If you mine specifications such as pre and post conditions invariant, you can feed them into formal verification again. This again indirectly depends on the ability to generate good system tests. Comparing behaviors. You have two versions of the program. What has changed? You can compare the grammars of their inputs. You can compare the grammars of the outputs. You can find out, oh, all of a sudden the new version accepts some input which has not been seen before. Is this new functionality, or is this something that actually doesn't belong in here? One of my dream things would be to find out the password actually is optional for the behavior. And I kid you not, this is what Apple had actually twice already, right? They just had it with the user interface, right? And 1 year earlier they had this thing with the SSL certificates, which they never checked. So yes, if you find out that whatever password, whatever certificate you provide is optional all of a sudden in a grammar, yeah, sure, deficits become obvious. Detecting abnormal inputs. You can use all these grammars to parse inputs as they come along, and you can deal with probabilities. You can figure out, this does not look like a normal string to me. And also, you can of course also use these grammars to protect against invalid inputs, because if you have mined what a standard request, a standard SQL query, a standard input should be, you can use the grammar to protect, to eliminate all other invalid inputs so far. And you can also apply this to inputs at the next level, because at the next layer in the program, you can protect this, getting inputs from other components that all of a sudden behave differently as before. So there's plenty of further applications. You can also come up with better debugging techniques, automated repair of inputs. You will have automated repair in a moment. You could go and say, I'm going to repair the input such that the program still works. I'm going to figure out what the difference is between input that works and that doesn't. So once you're able to reason about inputs in a similar way that you reason about programs, there's plenty of new applications here which we alone as a group probably will never have the time to really dig into. This grammar-based fuzzing, this is from outside already quite complete. We have this Tribble fuzzer, which is currently in beta. We use it internally, and we're going to release this to the world this spring. So this is coming up very soon. Our autogram tool, as soon as we have ported this entirely to C, this is something we plan to release late next year. And since I mentioned that, I'm currently giving a course on security testing. All these all of these techniques, grammar mining, grammar-based fuzzing, grammar-based mutation, all of these techniques actually fit the basic concepts of these techniques. Search-based testing too, fit into 100 to 150 lines of Python program each. Okay, just the basic concepts. So none of the super duper optimizations as Shiva showed the first. No, we don't. I don't teach this to students at this point. I just go with the basic concepts. And this actually makes a great common theme for a test generation book, and this is something me and my co-authors, I hope to bring Gordon Fraser into the loop, as well as Raoul Gopinath, my postdoc, Christian Holler too, who does the practical fuzzing, and we plan to write a nice book about this during the next year, and if all works well, this should be released again to the public in about 18 months from now. Okay, and with that, I think I'm over time already, maybe, I'm not sure.
I was paying attention and
okay.
talk most of the time.
Okay, good. And here's a short summary, and feel free to talk.
I'm sorry, I should have been paying attention.
Yes, I haven't paid attention either, sorry. So if you have any questions, let me know. Yeah. So if any questions, I'm happy to hear them. Thank you very much for your attention.
We have maybe time for one or two questions.
A small one. Context-free grammars have some limitations. So, for example, in your case, you cannot represent the fact that, for example, since you refer a grammar for a program that
yes.
Even when you refer to an array, then the number used to refer a position should be within the size. I'm just asking, since I worked on similar things and we had to use a different kind of model, did you have any experience or can you suggest a context in which this worked well? So, for example, maybe to refer a grammar for a program is perfect, or case studies that are not perfect?
There's two solutions to that. Solution number one is to come up with more powerful representations of languages. That is, we could go to context-sensitive grammars or even universal grammars, that is eventually Turing machines. But then you would end up with a formalism that is just as complex to analyze as the program itself. That's not where we want to go to. A more interesting way is to attach appropriate constraints to the elements of the context-free language. And there is a number of formalisms that allow you to do that. This would, for instance, allow you to say that when I'm synthesizing an identifier, I want to have an identifier that I have seen in a declaration earlier on. So when I'm declaring something, I can be as free as I want. But when I'm using something, I have to revert something that has been declared earlier on. Likewise, you can express that something has to be a checksum of an earlier element. Again, if you have an appropriate constraint language to do so, this is something we plan. So we want to keep the general structure of these programs context-free, because context-free grammars are easy to understand and easy to reason about, and these extra constraint pieces will then help you to generate syntactically valid inputs.
So let's move on to the next talk then.
Thank you.
Thank you very much.